So in this class, we will discuss about torsion of multiply connected thin-walled sections with an example. So here, to understand the concept, let us consider a thin-walled tube like this. The thickness of the tube is T. It is subjected to a torque T, and there will be a shear flow in the tube. So the effect of torsion is production of development of shear stress. As you know, there will not be any normal stress. It is production of shear stress. So that shear stress is expressed in the form of a shear flow. So that shear flow takes place like this along the circumference. So it is denoted by Q. So Q is called as the shear flow. Q is called as the shear flow, which is expressed in Newton per mm. That Q is obtained by multiplying the shear stress by the thickness of the tube. So actually this Q is a constant. That means tau and T may vary, but Q won't vary. It is a constant. So here you can see the units here. Tau is expressed in Newton per mm square. Thickness is expressed in millimeter. When you multiply, you are going to get in Newton per millimeter, which is a constant. So according to the theory, which is developed with Brent Batchow formula, here they have developed it. Now here I will consider an elemental area here. Elemental area here, dA is the elemental area. So this length of this arc, we can take it as ds, and h is this distance. So if you want this dA, elemental area dA, it is given by area of this triangle. Area of this triangle can be roughly taken as half into base into height. So half into base is ds, height is h. So dA is equal to half into h into ds, or h into ds is 2 times dA. So now we will calculate the torque, elemental torque. This dt is the elemental torque acting on this elemental area. So you know that torque is given by the force multiplied by the stress multiplied by the area we can take. So here Q into ds, so this is your force. It is acting at a distance of h. So force into distance, that gives the torque. So stress into area gives the force. That force into distance gives the torque here. Just like your moment. So I can take this Q into ds, that is shear flow, multiplied by this length, will give the force. So Newton per mm into mm will give in Newton. So that is the shear force, you can say, or shear flow multiplied by ds. This gives the shear force, you can get. The shear force multiplied by this distance h gives the value of the torque dt. So I can write this as Q into ds into h. This ds into h is nothing but 2 times dA. So therefore dt can be written as 2q into dA, or t can be written as integral of dt, that is 2 into integral q dA. So here I have written closed integral. It is a closed cube. Therefore I have used this zero symbol here. Zero means it's a closed integral. So in 2 into closed integral q dA, which is nothing but 2aq. So integral dA is a, and q you can take outside because it is a constant. So 2aq. So this is a very important formula. So torque in a thin-walled section is given by 2 times the area, bounded area, into shear flow. So 2aq. P is equal to 2aq. So please note that here this q can be written as tau into t. So t is equal to 2aq means t is equal to 2a into tau into t. Tau is equal to t divided by 2a. You can see tau is equal to t divided by 2at. So please see the units here. This t is expressed in Newton millimeter. A is expressed in millimeter square. This t is expressed in millimeter. So if you simplify that, you will get tau in Newton per mm square. So we have to stick on to these units when you are doing problems. So tau is called as the resultant stress at the boundary. So at this boundary, resultant stress is tau, and A is area inside the boundary. So this is the boundary. Whatever I have shown here, this shaded line, dotted line, within that area we have to consider. So please note that I have taken elemental area here. Total area becomes entire this thing. This is your total area. So this is the formula used to find the resultant shear stress at the boundary. Now from this formula you can see here, tau increases with increasing value of t and decreases with increasing value of t. That means, in other words, tau increases with t, and if you want to have tau maximum, t should be maximum, capital T, that is torsion torque should be maximum, whereas thickness should be minimum because it is in the denominator. That means you can say maximum shear will occur at this section where torque is maximum and thickness is minimum. These two conditions should be satisfied. So numerator should be maximum, denominator should be minimum. Then only you can have tau max. So therefore tau max you can write. So tau max is nothing but q by t, which is nothing but t max divided by 2a t minimum. So this capital T should be maximum, small t should be minimum. Then only you can have maximum value of shear stress in the case of thin-walled sections. Now another thing is we have to calculate this angle of twist per unit length. So two things are important. One is this shear stress, another one is angle of twist. Those two are the important unknowns. So theta is the angle of twist per unit length. So theta is given by this formula. You can derive this. Anyway, I am skipping the derivation. You can note down this formula. Tau t is nothing but q. Tau into t is nothing but q divided by 2ag. So g is called as the rigidity modulus or shear modulus, which will be in Newton per mm square for a given material is a constant, into closed integral ds by t. So this is important. How to take the ds is length of the tube. If it is curved in shape, we have to take the curved length only. Divided by t is the thickness. So ds by t we have to add. So integral means we have to add how many segments are there. For all the segments we have to take ds and t. That ratio we have to take and we have to add. Integration means summation only. So q divided by 2ag into a closed integral ds by t, that is the formula to find the angle of twist per unit length. So which is expressed in radians. So normally it is expressed in radians, of course, per mm. Per unit length means per mm. So that is the unit for theta. Now this can be understood by taking an example, simple example of a rectangular tube. So this is a rectangular tube with different thickness. So the length of the tube is 450, center to center length. You can see here, this is center to center length. The dotted line shows the center line of the tube. 200 mm is the width, 450 mm is the length. Thickness varies. So top it is 5 mm, bottom it is 5 mm, left side is 12 mm, and here it is 10 mm. So now we have 4 segments here. So I have marked it as 1, 2, 3, 4. This is the first segment. So for the first segment, width is 450 mm or length is 450 mm, thickness is 5 mm. Okay. For the second one, length is 200 mm, width is 10 mm. For the third one, length is 450 mm, width is thickness is 5 mm. For the fourth one, length is 200 mm, width is thickness is 12 mm. Now he has given, suppose if this is subjected to a torque of 60 kilonewton meter. If this rectangular type of tubular section, thin-walled section is subjected to 60 kilonewton meter torque, and if the shear modulus is 60 for 40 GPa. So 40 GPa means 40 into 10 power 3 MPa, Newton per mm square. We have to convert to Newton per mm square MPa when we are substituting the formula. So the question is, what is the shear stress induced in all these 4 segments? Tau 1, so tau 1 is the shear stress induced here, tau 2 is the shear stress induced here, tau 3 is the shear stress induced here, tau 4 is the shear stress induced here. So shear flow takes place like this. So shear flow, it takes place like this. Now we have to find out the values of this shear flow. So as I already told, shear stress is different, shear flow is different. Shear flow is always constant. Q is always constant, but tau and T may vary. So the product is constant, but tau and T may vary. Now the question is, we have to find out the shear stresses in all the 4 segments as well as the final theta, angle of twist of the entire section theta we have to find out. So we have this formula now. So using this formula we have to find out. So for finding shear stresses, we have to use the formula Q by T, where Q is constant, T is a variable, and for finding theta we have to use this formula. Now let us go one by one. First let us calculate Q now. The solution works like this. We have this formula T is equal to 2AQ. According to this Brent batch of formulas, T is equal to 2AQ. So we know the value of T he has given 60 kilonewton meter. So convert this into Newton millimeter. So 60 into 10 power 6 Newton millimeter is equal to 2 into A is this closed area. Please note that is the area of the area within the boundary. That is the inside, that broken line, whatever I have shown, central line. So within that is 450 by 200. 450 by 200 is the area within the boundary, into Q is the unknown. So from this you can find out Q. So Q will be equal to 16 to 10 power 6 divided by 2 into 450 200, which comes out to be 333.33 Newton per millimeter. So this is a constant value which is called as the shear flow in all the 4 segments. Once you get the shear flow value in Newton per mm, you can compute the shear stresses on all the 4 segments or walls of the 4 segments. So now let us take T1. T1 is the shear flow in the first segment, which is nothing but Q by T1 we have to take. So Q is constant here. T1 thickness of this first one is 5 mm. So 333.33 divided by 5, 66.61 Newton per mm square. Total is the shear stress in this segment or in this wall. Q by T2 we have to take. Q is constant, 333.33 divided by T2 is thickness of this, that is 10, you will get 33.33. Total is the shear stress in this. So Q by T3, so Q is same, 333.33, thickness here is 12 mm, so it comes up to be 27.7. So like this we have to calculate T3 and T4. So T4 we have to calculate. So once you calculate these shear stresses, so these are the values of shear stresses that are going to develop due to this torque in all the 4 segments. Please remember that the product of shear stress and the thickness is a constant, that is called as Q, that is the shear flow. Now coming to angle of twist, we can directly use this formula to find the angle of twist. So please note that it is given by Q divided by 2AG. So that formula I am using here. Q is 333.33, we have got that, divided by 2 into A is once again area within the boundary, 450 into 200, into G value we have to put in LPA or Newton per mm square, 40 into 10 power 3. So this is the constant value into closed integral ds by t. It has already told this ds is the length, t is the thickness for that particular segment. Now for all the 4 segments, we have to write the expression ds by t. For the first segment, ds is this length 450 divided by t is 5 mm. See, I have written here 450 by 5. Plus I have to, because integration means summation. So instead of writing sigma, we are using summation as integral sign. For the second one, length is 200, thickness is 10 mm, so plus 200 by 10. For the third one, length is 450, thickness is 5, so 450 divided by 5. For the fourth one, length is 200, thickness is 12, 200 by 12. So there are 4 segments. We have to add all those ratios. If you simplify, you are going to get theta as 1.003 to 10 power minus 5, very small value, radian per unit length of course. For unit length means it is per mm. So for 1 meter length of the tube, the angle of twist is 1.003 into 10 power minus 3 radian. So in each segment, you will have different values of shear stress values, resultant value of shear stress, but your shear flow value is constant. This is how we can evaluate the value of tau and theta for a simple, of course, this is simple rectangular tube. Suppose in this case, if they ask you to find out this tau max among these, whichever is highest, that is tau max. In this case, so this and these two are the highest values. So this is your tau max, because of course here your t value is constant. It is subjected to constant value of t, but the thickness is minimum for these two, first and third. So where thickness is minimum, we have the maximum value of shear stress. So toe max occurs in the first and the third segments in this problem. We will continue with this additional problem in the next class.